Hi everyone, this is going to be the second part of the permanent magnet synchronous machine drive lecture. So far we have learned the modulations, so the voltage source inverter modulation techniques. In this lecture I'm going to talk about inverter sizing, which is going to be a brief introduction. Then we will talk about how we can control the motor and which values do we need to measure and how we can use those measured values in the control loops. So when it comes to the inverter sizing, actually we need to know the characteristics of our load. And if we have a permanent magnet machine load, as the name suggests, then we need to know its power factor. So if we have a DC link voltage of 400 volts, DC link voltage 400 volts, and if we assume we have, for example, a 10 and 100 kilowatt system source, then it means that I can have an IDC, the DC link current, equal to 250 amperes. But how am I going to size the inverter? So on this side, I'm going to have the DC link, and I need to have a DC link capacitor, as we will discuss. Then we are going to have the inverter, three-phase inverter, because we have three-phase machines. So upper switches, lower switches, and so on. And I'm going to have the load. And in this case, the load is going to be a permanent magnet machine, but this discussions will apply at different types of machines too. This is going to be an AC machine. And here we have 400 volt, and here we have 250 amps maximum value. So as you know, so this inverter is going to operate like in the back mode, and the voltage at here in the AC machine is that here we have inductance and induced voltage, inductance and induced voltage, AC machine. Here is the neutral A. So VAN maximum can be set to VAN, peak can be set to 400 divided by square root of 3 if we assume a modulation index of 1 with the space vector modulation, or 400 divided by 2 with the sinusoidal PWM oscillation. This is its maximum possible value. But by changing the modulation index, we can change the voltages. These are going to be their maximum values. So it means that VAN can be controlled between 0 volts and 400 and 400 divided by square root of 3 with the space vector modulation. But in this case, we need to consider the characteristics of the load. So these are the induced voltage characteristics of the load. For example, if we have an AC machine, we talk about the power factor. So the AC machines are usually operating with a lagging power factor if you don't control them to work in a different operation mode. Permanent magnet machines can operate with high power factors, so it can be 0.9 to 1 or maybe 0.8 power, so depending also on the operation. And keep in mind, so our AC machine is going to be a variable speed drive. It means that throughout the operation, everything is going to change. So modulation index is going to change. The fundamental frequency is going to change. Modulation index, fundamental frequency. And moreover, the power factor is going to change. As the operating point changes, the power factor of the electric machine is going to change too. This is what I wanted to say. Assume that permanent magnets have a very high power factor, around 0.9. I cannot use just a single value because this value is going to change throughout its operation. So it means that an electric machine is going to have different power factors. So throughout this operating limit, torque speed characteristics, here the power factor is going to change. So power factor is not going to be constant. Assume it's going to be a high value. For induction machines, you can assume it to be lower than that, 0.8, 0.85, and for other machines it can be even lower than that value. But this is a quite high power factor for an electric machine. And in this case, we know that if I want to operate at the constant power, which is 100 kilowatts, the output power, if I neglect all the losses, is going to be 3 times V phase RMS, so square root of 2. As you know, we always use the peak values. This is the peak. Times I phase, this is also the peak, divided by square root of 2, multiplied by cosine theta. And in this case, I know the phase voltage because let's look into the maximum phase voltage. So actually, as the P out changes, we need to have different phase currents. Let's look at P out equal to 100 kilowatts and modulation index equal to 1. Modulation index equal to 1. In this case, I can calculate the I phase, and I phase peak value can be calculated as 1000 divided by 3 times 400 square root of 6, 3 multiplied by 2, multiplied by 1 over square root of 2, so I can get the peak value. Okay, this is division, multiplied by cosine theta. Assume it to be 0.9, so cosine theta. In this case, I can calculate the phase current, and I need to design my inverter based on this phase current. In this case, this phase current can be calculated as for the 0.9 power factor. So power factor being 0.9. Phase current, I phase peak, can be calculated as 320 amps. For power factor being 1, this I phase peak can be calculated 288. For power factor being 0.8, this can be calculated as 360 amps. So it means that if you are given the power rating of your source and the power rating of your electric machine, the current, how much current you are going to have in the phases, your phase current, and how much current an inductor has to carry at its peak power operation is going to depend on the power factor. So you need to know the power factor of your system, and you need to calculate the maximum required current based on that power factor so that you can size your inverter. In this case, this is a two-level type of inverter. As you know, each switch has to carry 400 volts. So switch blocking voltage should be 400 volts, at least for this example. This is going to be VDC, which is going to be 400 volts in our example. And as they need to switch VDC, but also keep in mind this DC link voltage is going to fluctuate. It is not going to be constant. It is going to fluctuate, DC link voltage, because of the SOC of the vehicle. So VDC is not a constant. And there are basically two reasons. The first reason is battery voltage is not going to be constant. Battery voltage will change with SOC. And the second reason is, so there can be some oscillations in the DC link. So DC link oscillations. This can be due to the transients, and this can be also due to the other components which are connected to the DC link. This DC link is going to be connected to some other components in the vehicle too. And during the transients, this DC link can fluctuate because of the other electrical components connected to the DC link. So this DC link can change since the battery voltage may change as the SOC of the battery decreases. And this DC link may also change as the other components ask for current or send back some current to the DC link, so there can be peaks. So therefore, we like to stay within the safe region. And if you have a VDC of 400 volts, actually, ideally, switch has to block just 400 volts. But we do select voltage rating for the switches, around 600 volts switches are used, because that DC link is not going to be constant, and we need to make sure that we have some safe region around this value. So there is most probably a rule, right? It should be like 2/3 of the blocking capability of the switches. So it is the first one thing is we need to select a switch which can block the DC link voltage in a two-level inverter. Moreover, we need to put some safety margin because our DC link is not going to be constant. So if, for example, during the regenerative breakings, this DC link can also go high if the battery cannot accept that much current immediately, or if we have some other components between the battery and the DC link. And based on these discussions here, we need to select the switch current. It's going to be based on the power and also the power factor. It's going to be decided based on the power factor of the electric machine. And if you have a low power factor electric machine, so you need to design an inverter with a high volt amp. So keep in mind, we design the inverters designed based on volt amps, not watts. So it means that actually we need to find out how much current should the switches carry based on the characteristics of the electric machine. So you need to check it throughout the operating region, all the power factor and the current required, and also you need to design your inverter based on the blocking voltage. And by doing so, you can select your switches. And as the power factor of the machine decreases, the kilovolt ampere ratings of the inverter is going to increase. So therefore, actually, we know that we need to be careful with the power factor of the electric machine. If the power factor of the electric machine is decreasing, actually there is no disadvantage for the electric machine, but it's going to be very disadvantageous for the inverter as its size has to increase. So the next design thing is, so the first we need to design these switches. And we already talked about the switching frequency. Maybe it is good to repeat it here. We learned that the switching frequency has to be at least 10 times the F fundamental maximum. So it's higher, the better actually. So this F fundamental maximum is going to correspond to the fundamental frequency at maximum speed. And I have done it many times, but if, for example, we have a maximum speed of 12,000 RPM, then we need to calculate the fundamental frequency. The fundamental frequency is going to be that divided by 60 and multiplied by the pole pairs, because this is going to be electrical frequency. And based on that, we need to select a switching frequency. And if we know the voltage rating, current rating, and switching characteristics that we require, then we can select this side of the inverter. So this is maybe the third important thing, switching frequency, so that we stay within the loss limits. And we already talked about how we cool the inverter, and the cooling of the inverter is also quite important. So the next topic is going to be the DC link capacitor, how we size the DC link. Normally, these DC link capacitors in electric vehicles, they depend on of course, many things, the DC link value, or they also depend on the used electric machine, so many other things. But usually, if you check, if you look in the internet, the DC link capacitors are around 500 microfarads, just 500 microfarads, or a little less, to 1000 microfarads, or a little higher. So here we are going to have the image. And for sure we need this capacitor, because actually, so this is a DC site, so this can only supply the active power, but here we are going to have some power factor, and we also may need the reactive power. So therefore we need this capacitor. If we don't have this capacitor, actually we cannot supply for the reactive power of the inverter. So of course this is going to depend on the voltage rating, power rating, and frequency, voltage, power, frequency, and what else? It's going to depend on the voltage, power, and frequency, and power factor of the load or of the system. So you need to decide it based on that. But if we try to understand why we have this DC link voltage, we can just make a very easy example. So you have an idea why we need this DC link voltage. Assume that modulation index is 1. So we don't come close to 1, but usually come close to 1, 0.95, 0.96 maybe. And on this limit curve, we know that on this row here, we are going to be on the modulation index equal to 1, or very close to 1. Modulation index is equal to 1. So this is going to represent the operation at this curve. But here, under this part, the modulation index is going to be less than 1. So it's not going to be as high as 1. We are just looking at this limit operation. And at the limit operation, we also know that power is going to be, P out is going to be P max 2. So therefore, I have just chosen it. Assume that power modulation index is 1. Power is going to be P max, that's assume 1000 kilowatts. And moreover, power factor, I'm just going to assume it 1. So which is going to be a value, which is going to be a value. So it means that the current, phase current in the inverter side, phase current and phase voltage are in phase. So we are looking in such a situation. And in this case, at the output we have 100 kilowatts. 100 kilowatts is going to be 3 times, and assume we have space vector modulation, space vector PWM. It is going to be 400 divided by square root of, so anyway, I have already done it. So square root of 6 multiplied by, I phase square root of 2 times 1, because my power factor is 1. And in this case, I phase is going to be 288 amps, as I have just discussed in 2 slides before. But my DC link voltage, as we calculated, this can be only 250 amps in its maximum value, because my DC link is 400 volts, and here I can just apply 1000 kilowatts. But the inverter phase current, and it means that if I just put the inverter here, the inverter phase current that has to pass through these phases this is going to be 288. So here we are going to have 288 amps. But the DC link can only supply 250 amps. So it means that actually throughout this duration, this extra current has to be supplied also by the DC link. So the DC link capacitor, otherwise we cannot have that much current. So for example, if the power factor decreases, then this current is going to increase, as we discussed, 220 or 360. And it means that actually we need to ask for more current from the DC link as the power factor decreases. So what is happening is actually So we are just asking for a pulsed voltage, and this current is going to come from the DC link or from here, but during the active stages. And for example, if we select an operating point, if we select an operating point which corresponds to the peak voltage, so phase A, peak voltage, so this is phase B, and this is phase C. Whatever, it's really nice, but it doesn't matter. So here, if you operate at that point, let's assume that, and as we discussed, this is going to be correspond to the V1, if this is phase A, the vector of V1. And if we want to get the maximum possible voltage, which is 400 divided by square root of 3, this is what is the peak value, this is not the RMS value. What we know is the turn-off time of V1. If we turn on V1 for TS, if we turn on V1 for a period of TS, then we would get at the output 2 over 3 VDC. However, at the output, we want to get only this much VDC over square root of 3. So that means then V1 turn on duration must be TS times square root of 3 divided by 2. So that divided by 2 multiplied by square root of 3, that V1 duration is going to be that much. And the rest of the durations, the rest, TS minus TS square root of 3 over 2 divided by 1 over 2. This is going to be divided between T0 and T7, turn on duration of the zero vector, turn on duration of another zero vector, which is the sum. So it means that during that much time, TS square root of 3 over 2, I need to get 288 amps. But on the rest, during the other time, so during this time, this is going to be the connection, first one is going to be the up. But in the other time, I know that, oh, here, this one or this one, right? So this is going to be freewheeling states because I'm going to disconnect the load, the electric machine from the load. So we can therefore call it freewheeling stages. And in this case, what is going to happen is during the turn on active stage, we are going to ask more current. And higher current than the DC link is going to be supplied by the DC link voltage, DC link capacitor. And during the off times, because we are going to have an off time, DC link is going to be filled, DC link voltage is going to be filled by the battery. So it means that surplus current is going to be asked from the DC link, and then the DC link is going to be filled by the battery system when during the freewheeling stages. And this is a more detailed topic, actually, how you calculate the current coming from the DC link. And we would like to actually make sure that our DC link voltage is not fluctuating a lot. So this DC link voltage is more or less constant. And if you want to have it here, a constant DC link voltage, what you can do is you can place here a very big capacitor. So one choice is to put here a very big capacitor so it doesn't fluctuate much. So this could be one solution, but on the other hand, we don't want to have a very big capacitor, and we want to implement a minimum possible capacitor, but which is still fail-safe. So in many papers, actually the capacitor is one of the most problematic components in an inverter, in an electric vehicle. So the capacitor should be designed so that it doesn't fail. It is very prone to fail. So it means that you need to select a capacitor should be big enough so it doesn't fail. So one of the most problematic components is the capacitor. So you can put there a small capacitor, but because of the high AC currents, the lifetime, lifetime of your capacitor will be short. And the second is it shouldn't be too big because it is going to add to the space required. So they require lots of space, the capacitors. So therefore you need to make sure it is not taking so much volume, much space, and of course the nesting is the cost. So you need to find an optimal design for the capacitor so that it doesn't have a high voltage ripple or a high voltage ripple, so its lifetime is good. But on the other hand, it is not too big and not too costly. So the capacitor design is actually important, and I think in most of the applications, the capacitor design is done by using the simulations, and they try to keep the voltage ripple on the capacitor beyond the given value. And of course, you need to consider the torque speeds, the voltage, power, frequency, and power factor distribution throughout the torque speed characteristics. So there is a paper which you can refer if you want to work on the capacitor sizing. So they have calculated the capacitor current, which I'm going to show. DC link capacitor current. So here is the system. Here it can be an electric machine, it can be a power system, it can be anything. So, but they all have also done it for the electric machine. They haven't considered the frequency change, but I think the frequency change is a little more straightforward than the others. So here is the capacitor current, here is inverter current, and here is the load current in an electric machine, electric vehicle, of course. Here we are going to have not the strict fire or so on, but we are going to have here the battery. So a constant DC linked value, which is going to change with the SOC of the battery or loading of the battery. And they try to understand the ratio of the RMS current going through the capacitor, RMS current, the fundamental of the RMS current, and the RMS current of the here, one phase, they are going to be the same, all of them are going to be the same, as a function of here the modulation index. They go all the way to 150 to account for the space vector modulation, I suppose. And here it is the power factor, the effect of the power factor. As you can see, here it is, first of all, this is the ratio. It means that as load current increases, then you need to multiply these values. That means that as the RMS current required is high, this value, if you IC RMS, is going to increase. And if we have a modulation, as the modulation index increases, so these are different power factors. So at different power factors, we are going to have a different behavior. At the highest power factor, the maximum IC RMS to the load current RMS, so electric machine RMS, comes around somewhere 0.6 in this region. But here, very important again, all these values has to be multiplied to get a real value, not a ratio. You need to multiply it with the load current. So, as for example, in an electric motor, if you are operating, for example, here, you are going to have let's operate over the max. If you are operating here, so you are going to have a modulation index around 0.5, but a high current. Or you can operate here, your modulation index is going to be even lower, but you are still going to have a high current. So if you are in the red curve, let's assume it's 0.2, you are going to be somewhere, the modulation in this, assume that the power factor is constant, 0.8, and the modulation index 1 has 0.2, and the other one is going to have a modulation index around 0.4. So here, assume, I should write it somewhere, assume PF equal to 0.8. But if you compare these 2 points, the blue point is going to be worse compared to the red point in terms of the ripple. And this is because that the current is kept constant, but what we know is the modulation index has increased. Moreover, the power factor is going to affect, and again, here's the same thing, here is the ratio. So if you have a low modulation index, or if you have a high modulation index, the ratio is going to change. And for example, again, if we compare them to the 0. We put it somewhere 0.2. And power factor we assumed, doesn't matter, both sides are same. Let's put red to here, and the other one I'm going to put somewhere here. So as you see, in this case, we are also going to have, they should be made at the same values. I will just put it from this time. And here is also a 3D graph of that, and it shows that as modulation index increases, usually the current ripple in the capacitor increases, and as the power factor is changing, this is 0 to pi, so this is 0, it means there's no power factor being 1, is going to also affect. So if you want to design the capacitor, as I said, you need to make sure that it is big enough so that it doesn't fail, but on the other hand, it is small enough so it doesn't occupy much space and it doesn't cost much. So this is a very critical decision, how we decide on the capacitor, and you can also decide it with some rules. So after that, I want to talk about the motor controller. So we have learned how the inverter operates, we have learned how the permanent magnet operates, and we have also learned here stands for the space vector modulation, how the space vector modulation is. And actually we have learned all these blocks here, how the field oriented control works. So just to start with, I want to say a few words to the field oriented control. In short, we call it FOC. And FOC is actually a way of control. And in the FOC, we control ID and IQ currents. And ID is called as the field generating current, and IQ is called as the torque generating current. And we separate them, and they are going to be both DC quantities. And if this is the case, actually, it is going to be the same as the control of a DC machine. So we are controlling an AC machine just like a DC machine. So in the DC machine, we had the torque generating component, which was the armature. Maybe I can just write it here. So if we have the brushed DC comparison, IQ represent the armature current, which we control, and ID represent the field current, which we control to adjust the field. So we are orienting ourselves with respect to the field. So that's why it is called the field-oriented control. And this can be applied to all types of the AC machines. If you have an active field, you may want to have an ID equal to 0 because you already have a field generated by some other source, which can be the permanent magnet or the DC excitations, because these are just the stator currents. So in the field-oriented control, we are going to control the stator currents, and we are going to have its two components, which is one is going to control the field, and the other one is going to control the current. If you have already some field with permanent magnets with some DC excitation winding, you can set ID to 0 and just supply IQ. But in most of the electric machines, like induction machines and some synchronous reactance machines, you must have an ID to be able to get the torque. because if you don't have an active winding or actively supplied winding or a permanent magnet in the rotor, you also need to create the rotor field by the stator. So that's why you may need both of them. So depending on the machine, you need to decide how much ID and how much IQ you require. Then you need to have control loops to control it. And to be able to do SOC, you need to have some measurements. The most important measurement is the position. So here we are measuring the rotor position. This rotor position is going to be used in transformations and also to be able to decide ID, IQ. So here are the ID and IQ values. And this ID and IQ values are decided based on the torque reference and also the speed, actual speed of your electric machine, the mechanical speed. So this mechanical speed can be measured by the position sensor, or it can be measured with no sensor, it can be estimated, but in high performance applications, position sensor is used. So in electric vehicles, we do use position sensors. They all use the position sensors, because if you estimate the position, there will be small errors and it will deteriorate the performance of your electric machine. So I'm sure that there are studies which are working on the sensorless control for electric vehicles, but I think most of the electric vehicles on the market, they do have a position sensor. So to get the speed, we need to take the derivative of the position, so that we can get the speed. So once you have the position sensor, you can also calculate the speed based on the position. So here, the optimal current reference generator is actually taking the machine characteristics into account and machine type, machine characteristics into account to be able to operate at that operation. How much ID and how much IQ do I need? So this is actually what the field-oriented control block is going to do. We're going to decide on the ID and IQ value. And after that, the current controller is going to generate some voltage references, because we have a voltage source inverter, and to be able to control the inverter, we need some voltage input. And here we are going to have VD and VQ references. And maybe I shouldn't put anything. So VD and VQ reference is going to be here. So these terms, which I'm going to show in the next slide, are actually going to be some VD feed forward term, and this is going to be VQ feed forward term. So we are just going to help the current controller. Here are going to be PI controllers. In the current controller, we are going to have PI controllers. And in the PI controller, we need to get these are references and ID and IQ value. ID and IQ value, which are going to be measured. And we are going to apply PI controller based on that, and with some help coming from some other loops, as we will see from next. We are going to get the VD reference and VQ voltage reference. Then, to be able to apply space vector, as we discussed, we need V alpha and V beta. So therefore, here we are going to apply the transformation, this cosine, sine, the inverse transformation of it. Actually, I'm going to apply cosine, sine, minus sine. Cosine was the regular transformation. We are just going to apply the reverse transformation to be able to get alpha and beta. Here, to be able to get ID and IQ, so these are not real values, those you cannot measure, you can just calculate it from the measured quantities. We are going to measure all the currents, IA, IB, and IC. For IA plus IB plus IC being equal to 0, it is also okay just to measure 2 of them. 2 measurements are enough, but you can also measure 3 of them just to make sure that you have some extra measurements in your system. 2 measurements are enough. And from that, you need to first change them to I alpha, I beta. Then you need to change them to ID and IQ. Here you are going to apply 2 over 3, 1 minus 1 over 2 minus 1 over 2, 0 square root of 3 minus square root of 3 all divided by 2 matrix to get I alpha, I beta, and to get DQ you need to have, which I'm going to write here, sine, sorry, it's going to be cosine. This is going to be cosine, sine, minus sine, and cosine theta transformation. So here, as you see, you need the transformation with respect to the position. So therefore, you need the position information, and here you also need the position information, and these should be the electrical positions, not the mechanical positions. So as you see, if you know what is happening, it is very easy to understand the control loops. And usually in an electric vehicle, the driver is going to do the speed control, the police will do the speed control. And based on the gas pedal position, we will have a torque input. So in the next 2 slides, I will also just repeat the same for some other loops. In this case, I also included an speed control loop at the outer part, but most of the time you don't need it. So you can just avoid it because, as I said, as a driver, you are going to be in this loop. You will check the speed of the vehicle and you will check the traffic and you will decide to speed. If you want to accelerate, you will ask for more torque. Actually, this part will be done by the driver. The driver will make sure that the outer loop is closed. And hopefully the driver will act wisely. The MAM measurement is we need to measure the speed or position, let's call it mechanical position or electrical position, so that our sensor can directly measure the electrical position. Then this position is going to be used in such blocks, so this is going to be electrical position and electrical position, as you see. Then to close a speed loop, if you want to have a speed loop, then we need to take the derivative of the position so that we can get the speed. But of course, if you want to have the speed control in RPM, it was given as RPM, so we need to change it to divided by 2 pi multiplied by 60. Moreover, we also need to divide it by pole pair numbers. So this is the mechanical value. So if this was electrical, then you need to divide by pole pair number and so on. But here we all use it, so therefore let's assume it was electrical. This is how we designed the sensor. It directly gives us the electrical position. Automatically, this was the electrical position. So here, one important thing is ID was set to 0, but you can also set ID to any other value. So the system, it is going to be also regulated in the closed loop. So this was done for surface mount PMSM, so it is easier. For the IPMSM systems, so this optimal current reference generator can include some lookup tables, so that based on the operating point, then you can decide on ID and IQ. Assume that we want to get ID equal to 0, but it could be ID equal to 10 or 20, something like that. If it's from the space vector modulation, from the torque, we can divide the torque by 1 over, we know that 3 over 2 pole pair number flux PM times IQ. To be able to get the IQ, then we can just divide the torque with this 3 over 2 pole pair number flux PM minus 1, so that we will get the required current IQ. And the variables we need are the pole pair number are required and flux PM required. And if it's not a 3-phase machine, we also need to know the number of phases, but assume it's a 3-phase machine. So this limiter here is important because the system can ask for so much torque and we need to limit it. And here we need to set a maximum value of IQ max or IS max, the maximum current should be limited by the system. So even if this part asks for 1000 amps, we are not allowed to supply 1000 amps. So therefore we can use here a limiter. And now we reach the IQ reference. We already had the ID reference. So, but as I said, these can be directly the outputs of this block, ID and IQ. From here, we are going to have the IQ value and ID value, which is calculated from the measured quantities. And as you see here, there are just two measurements, IA and IB, because we know that IC is going to be minus IA minus IB. So they need to be added up to 0. And the first transformation is going to be ABC to alpha beta, 2 over 3, 1 minus 1 over 2 minus 1 over 2, 0, square root of 3, 2, minus square root of 3, 2. This is going to be the first part, and I will get alpha beta. From alpha beta, cos theta, sin theta, minus sin theta, cos theta. This transformation can be done. So these are all electrical positions, so that I will get ID and IQ. So I cannot measure ID and IQ, but I can calculate it with the help of the position. Here I need to have the position information, and so this will be used to apply the PI controllers. For example, for the IQ is coming here. Here is the IQ coming from the measurements. So I'm just going to have the PI controller to control the IQ. This is going to be the first thing. And I will have the same thing for the ID. ID measured, minus sign, and there's going to be the PI control. So actually the rest is going to help my VD and VQ approximation, VD and VQ calculation. So what we know is from the VD and VQ characteristics, first of all, they are going to depend on their own current with the resistor drop. Then there can be some inductance, the IDDT, LS, and LS. Let's keep LD and LQ, so it is more general. LD, LQ, DIQ, DT. So these are going to be only for transients, plus or maybe minus. So when we look at the phasor diagram, actually, so this is D, this is Q. But we know this induced voltage is going to be always in Q axis. This is E. This is going to be actually omega E flux PM, because it is the derivative of the flux PM, the flux linkage. The flux linkage due to the rotor is going to be in the D, so that's where induced voltage is going to see in the Q. And let's write it, omega E flux PM. And moreover, if we have some Q current, its effect is going to come in the minus D axis, omega E LQ IQ, in the minus D axis. And here, therefore, I'm going to add here a minus omega E LQ IQ, because if I have Q current, it's going to affect D axis. If I have induced voltage, it's going to affect Q axis. And if I have any D current, so I'm not going to send any positive D current, but assume if I have any positive D current, its effect is going to be seen on the Q, omega E LD ID, in the positive way, omega E LD ID. And so actually this was my VD/VQ calculations. And for example, if I have ID equal to 0 and ID equal to 0 and IQ equal to non-zero, this is going to be my induced voltage. This is going to be omega E LQ IQ. And for ID being 0, this is going to be the phase voltage, Vs. And Vs is going to be the VD plus J VQ. So this is going to be my components. Now in the control loops, I'm just going to add these, the resistance and the transient term. You know that ID, IQ are DC values, so this derivation is going to be 0 at steady state. So the first one are SLQ. So I'm just helping the voltage calculations because this is going to give me the voltage rating here at the output. So therefore here RSLQ is for this first part, which is written in the black. Let's save, which is written in the black in this part. And this part here, which also helping PQ, is going to include this induced voltage term. So flux PM, I have written it, which color? Green color. Flux PM times omega E. So I'm just adding it. So I'm just trying to get some references for the VQ. So the VQ is calculated by flux, this part, plus omega E flux PM, and do I have any other parts? And maybe we can also add the other components. Let us finish the DQ part. So maybe we should also add it. I have just written it wrongly. And we need to also add, okay, I understood why it's not here. So we also need to add the component, which is going to be the orange component here. So let me do it with the orange. Omega E LDID term also can be added. So here represents this equation, EQ equations. But in this example, ID was taken as 0, ignored, since ID was equal to 0. That's why it doesn't include it. Otherwise, we could include that here too. And at the VD reference, we can have the controller, which is going to control the ID. Moreover, here we need to add now the omega E times IQ times LQ. But it should be minus LQ. Omega E times LQ times IQ must be added. Omega E times IQ times minus LQ must be added to get the VD reference. So what we try to do is from ID and IQ reference, we try to get VD and VQ reference. Once we have the VD, VQ references, just here we can apply the inverse transformation with theta so that we will get alpha beta. And here we can also apply the inverse transformation of what we have here. Let's say alpha beta to ABC, and we can get VA, VB, and VC, just the inverse of this part. And if we have here 3 reference values, VA, VB, and VC, it means that it cannot be space vector modulation. So it should be sinusoidal PWM. And as an output of sinusoidal PWM, we are going to have the gating signals. So we are going to have the gating signals of the 3-level inverter. Okay, so basically in the control loops, we are trying to have a PI controller to control the ID and IQ, plus we apply feed-forward loops that's going to include the terms here in this equation, so that the system will less depend on the current and will less depend on the speed, because these quantities all depend on the speed. And if we add them as a feed-forward loops, then we will make sure that our controller is going to be same throughout the operating conditions. So here it was for the sinusoidal PWM. The same thing can be done for the space vector PWM. Now the input should be alpha and beta, and if you do it on alpha beta, it's space vector modulation, and the output blocks is going to be the gating signals. So between the sinusoidal PWM space vector modulation, the only difference is space vector modulation will be applied in alpha beta, but sinusoidal PWM will be applied in the ABC frame. And to be able to do these control loops, we need to measure the DC link voltage, because this is going to actually show us how much current or do I need to supply, how much voltage I can supply, because it is going to be variable, which is not shown in the previous cases. So if it's 250 volts, or if it is 350 volts or 400 volts, as the SOC changes, then I need to actively know the DC link voltage. Anyway, it will be known. At least two of the three-phase currents, IA, IB, and IC, two of them, so that I can calculate ID and IQ, which are going to be regulated. Moreover, I need to have the position, and by taking the derivative of the position, I can get the speed, electrical speed or the mechanical speed. So this is important. So the position sensor, as a position sensor, we need to have an absolute type of the position sensor. And those type of position sensors are called resolvers. And in most of the electric vehicles, we do use a variable reluctance resolver, as I'm going to introduce. On the other hand, you can have sensorless or self-sensing position estimation. Let's call it estimation. To do that, you basically have two ways. Like, we can do high frequency signal injection or model-based position estimators, or you can combine them both. But in the electric vehicles, we do have position sensors, and most probably these sensorless algorithms are applied just in case if something goes wrong with the position sensor. So the basic operation of the resolver is explained here. So this is going to, there's a rotating part, and the coil is going to be rotated mechanically, and you are going to supply a high frequency signal. High frequency signal is going to be injected to the coil. This is going to rotate, and there are going to be two coils, sine coil and cosine coil, and they are going to be stationary. They are not going to rotate. Stationary. And there is going to be transformer effect between these two. And if you check these equations, actually in the gap we are going to create a rotating field because of the rotation, and of course also this rotating field is going to have a varying amplitude in the air gap. And if you see the voltages, the voltage in the Q in D is going to be the derivative of the first part. This is due to the high frequency signal injection. This is due to the rotation of the rotor, and we can say that it's related to the omega m times t. So this is the mechanical speed. Then UD can be calculated like that. The derivative. This is also going to be depend on the time, omega m times t. And the other one is also going to depend on time. We can take the derivatives. And if you do that, actually, this omega f is going to be much bigger than the omega m. Therefore, the first components are going to be dominant. So the second components are going to be low. This is high frequency. That's why it's called high frequency. And in this case, in the UD, you are going to see such a signal, and in the UQ, you are going to see such a signal. The signal says that actually this is going to be basically a cosine in the UD. It means it is going to be basically a cosine. But its amplitude is going to change with the sine function. So it means that it is amplitude is going to change. So something like that. So this is not nicely drawn, but its envelope is going to be a cosine function, because whatever happens, so here it is going to be also not that high. So here it's going to be high, it comes to 0, then it grows from the 0, then again to 0, and something like that. So it's going to be UD. And UQ is going to be the same, but it is going to be in the form of the sine. This is amplitude is going to change. So here it's small, and it's going to increase. So is going to be something like that, from which the envelope is going to be signed, but the sign amplitude is going to change. And from these two signals, we can calculate the position. Actually, here you can see, so one is going to change with the cosine, its amplitude is going to change. The other one is going to change with the sine, its amplitude is going to change, and based on these two values, we can calculate the position. So there are basically two types of the resolvers. One, so first of all, we don't want to have brushes going to the rotor, to the rotating part. So you can use a rotary transformer, or you can just induce this current in the rotor by the induction. Then you can just do the same. The cosine and sine cases can be here, and this part can be just used to supply high frequency voltage to the rotor. This can operate like that. But in the newer versions, actually, so these are the basic resolvers as they operate with what I explained. But in the recent versions, we have the variable reluctance resolvers. In the variable reluctance resolvers, rotor does not have any excitation. Rotor, no excitation. But it has some variable reluctance here. You can see four low air gap regions. It can be 3, or there can be different shapes. And from the stator, we are going to both have sine values and cosine values. Here you see that actually there are going to be 6 outputs. One is going to be for the high frequency injection, one is going to be sine, other one is going to be cosine. In all of these teeth inside, there is going to be the high frequency injection, and on top of it, the collector winding. So maybe it is shown here. So on the teeth, first we are going to have the high frequency, and then depending on their position, then we are going to have on top going to be the collector winding. It's going to be sine winding or the cosine winding. And by looking their phase shift between sine and cosine, we can find out the position. So actually, even if it is standing, you can calculate the position. Okay, here you can see there are just 6 terminals from all of them. Okay, so these are usually used. I think in most of the electric vehicles we do have that. This will be placed onto the shafts, and this is going to rotate, and this will be mounted on the electric machine housing, and it can detect the position and the speed. Okay, it already has been a long lecture. Let's finish it. So in this course, not just in the lecture, we talked about different electric machine types, and we said that we have permanent magnet machines, which are the IPMSM types, which are used for the electric machines. IPMSMs are used, and we have some induction machines, which are few, but we expect to have more machines with reduced permanent magnets. Trend is going to be with reduced PM or no PM. We want to see electric machines with less permanent magnets or reduced or no permanent magnets. Currently, the voltage levels are 400 volts, and the trend is to see an 800 volt so that we can do the fast charging. Power, speed, and torque specs depend on the vehicles, but we see powers around 120 kilowatts to 160 kilowatts. But these are the peak powers. The continuous powers are going to be less than that. Speeds tend to increase, not like we have seen some vehicles with 17,000 RPM. You can say that now there are a change between 13,000 and 17,000. We don't expect a big increase in the speed because mechanically it is going to be very hard to increase the speed. Winding technology, we have the regular wires, regular round wires, and we have the hairpin technology, hairpin, such tools. And we expect to see both of them. But we are seeing more and more designs with the hairpin technology. Materials, we see that actually we want to use permanent magnets with no rare earth, or we want to maybe we can use aluminum as the rotor conductors, but in the short time we don't expect any big change in the materials. Maybe in the inverter we can see the silicon carbide technology. In the permanent magnets we can see no rare earth neodymium magnets, neodymium ferroboron magnets. And the cooling systems, they are going to be integrated, and it means that EM plus inverter is going to be used one cooling system, and we try to make them more effective. I think this they are also going to stay as they are for a while. Okay, here are some references for the pulse width modulation, for the RMS current of the DC link capacitor calculations, and there's also a video, let's say not assignment, just a video for the field-oriented control. Okay, thanks for listening.